In this module, we will learn how to model mechanical systems from first principles. Previously, we had learned how to analyze differential equations representing physical systems and how to solve differential equations using the Laplace transform. In this module, we will specifically learn how to generate that differential equation for mechanical systems. The structure of the lecture will follow the outline shown. We'll talk about the different types of elements that make up a mechanical system. We will go through some examples, and then we will talk about how motion is transmitted and converted using gears and pulleys and things like that. Here are two example mechanical systems. The bottom system is a translational system, and then the one above it is a rotational system. We will do both. Each type of system consists of three basic types of elements. One, inertia elements, such as the mass or rotational inertia shown, spring elements, and damper elements. And as we discuss these, the spring elements and the damper elements don't literally have to be springs or dampers. Even a solid bar of steel has stiffness properties and damping properties. Inertia elements are in essence the mass in a translational system, or the mass moment of inertia in a rotational system. Each inertia element with its own independent motion needs its own differential equation to describe its motion. And we will use two sort of approaches for deriving the differential equations. One is Newton's second law, which is F equals ma, and then sort of a rotational version of Newton's second law, which is also a form of Euler's second law, sum of the moments equals J alpha. It's interesting to note that inertia elements store kinetic energy, and that can be proven below, where energy is power integrated over time in essence. This isn't something that we're going to use in this class, but if you were to go further and look at modeling systems using state space form, considering where energy is stored in the system can help you derive the state equations for a system. Another type of element common to mechanical systems are spring elements, where the force or torque is generated to resist deflection. Examples of this include springs, but as I said previously, even a steel rod has stiffness. If a steel rod will deform and try and return to its original shape. Again, considering the energy aspect of these elements, spring elements store potential energy, which can be useful if you're trying to derive the state equations of a system. The way that we will typically model the force generated by a translational spring is using Hooke's law. That is, the force generated by the spring is proportional to the deformation of the spring. So if we look at this figure, X, capital X, is sort of the undeformed length of the spring, and the total deformation of the spring is the difference in the motion between the two ends. So X2 describes the motion of the left end of the spring, and X1 describes the displacement of the right end of the spring. Therefore, the total deformation of the spring is the difference between the displacement of the two ends, X1 minus X2. Looking at the spring, you can sort of imagine that if you compressed the spring, it would generate a force to sort of push back on you on both ends, and that's how we're going to model things. So if I compress the spring, a force F will push back on each end. Alternatively, if you were to stretch the spring from its undeformed length, if you were to stretch it, then you'd have equal and opposite forces pulling in on the two ends of the spring. This type of model of a spring, using Hooke's law, is desirable because it's a linear model. The force generated is linearly proportional to the deformation. In reality, all springs are nonlinear. If you stretch the spring far enough, it will, in essence, start to take a set. It may deform plastically. Even though that is the case, this linear type of model tends to work pretty well as long as the deformation isn't too large. If you sort of zoomed in on the origin of this graph, where you were looking at smaller amounts of deformation, the nonlinear graph and the linear graph would sort of lay on top of one another. They'd be very close to one another. Torsional springs we can model in the same sort of manner, where the torque being generated in this case is proportional to the sort of the angular deformation of the spring. So you can sort of imagine this spring as being twisted, where the two ends of the spring are moving with different amounts of displacement, and the torque generated is going to be proportional to the difference in the displacement of the two ends. The last type of element that we will include in our mechanical system models are damper elements. And damper elements, they model how a force is generated to resist motion. And examples of these are dashpots, friction, and wind drag. For example, you can consider if you have an object that's sliding on a surface, friction will be generated to oppose the motion of that object along the surface. Similarly, if you have an automobile moving through air, there will be wind drag generated to oppose the motion of that automobile. Here's an example of a dashpot. This symbol you can sort of envision as being a container filled with some viscous fluid, and a plunger separate of that container that's trying to be pulled through the fluid. And so as you attempt to pull the plunger through the fluid, there's some resistance that's developed, and that resistance is proportional to the relative velocities of the two ends. And so that's what's shown in this equation here. The force generated is proportional, where B is a proportionality constant between the difference in velocity of the one end and the other end. You can imagine if the two ends were moving together with the same velocity, there would be no resistance generated. In essence, the plunger and the fluid would be moving together. You only generate resistance when you try and pull the plunger through the fluid. Analogously, we have a rotational version of the dashpot where the torque is being generated such that it's proportional to the relative angular velocities of the two ends. Again, thinking about how energy relates to a damper element, a damper dissipates energy, so it doesn't store energy, which is different than the inertia elements and the spring elements. In the previous slide, we saw a model of the force generated by a dashpot, and that model was linear, sort of like this model over here, where the force was linearly proportional to the difference in the relative velocities of the two ends. This kind of model also represents a viscous friction model, where the friction generated is proportional to the velocity along the surface. Again, we like this type of model because it's linear. Another type of friction model is a Coulomb friction model, where you have this stiction such that when you try and move an object relative to another object or a surface, it's initially going to stick. And so there's force that's being generated without any motion when the velocity is still zero. But as you increase the applied force, eventually it breaks free. And then at that point, the force is constant. And the direction of the force changes whether you're the direction that the object is going. And so this is a nonlinear model of friction because of the jump. And then here's an example of of a typical type of model for wind drag, where wind drag tends to be proportional to velocity squared, where again we have this sort of nonlinear model. As was mentioned previously, nonlinear differential equations are difficult, if not impossible, to solve analytically. So when we can, we will try and use a linear model. When a linear model isn't sufficient, we will discuss some ways to sort of analyze nonlinear systems. Here's another example of a frictional torque model that's more accurate than either the viscous model or the Coulomb friction model from the previous slide. It's more accurate for most situations in that it contains aspects of both types of models. So we see that the friction, the torque, is linearly proportional to velocity, where here omega is angular velocity. So the faster it's spinning, the larger the force is. But there's also a stiction element to it, which was discussed previously, where it'll initially stick before it breaks free. In this sort of more realistic type model, we will actually see examples like this when we do our laboratory activities. In summary, when we want to model mechanical systems, i.e. when we want to generate the differential equations representing the mechanical systems, we're going to follow this approach. First, we're going to choose a coordinate system and an orientation. Then we're going to draw a free body diagram for each inertia. When we do that, we will note various assumptions, assuming viscous friction or assuming a linear spring, things like that. Then we will generate the equations of motion, i.e. the differential equations, using these two equations we showed previously, Newton's second law on the left and the rotational version of Newton's second law. And then finally, we will attempt to double check our results to verify that our equations of motion, our differential equations that we've generated, make intuitive sense. We will now go through some examples demonstrating how to apply the approach that we just put forth for modeling mechanical systems. The first example that we'll do is a translational system, a quarter car suspension. This diagram over here is a representation of a car suspension. M2 is 1/4 of the total mass of the car. It's the sprung mass. It's the mass supported by the suspension. Here, the suspension will be modeled as having some damping B and some stiffness represented by the spring constant K2. M1 is the unsprung mass. It's in essence the mass of the wheel. And then we will model the tire as having stiffness K1 with negligible damping. Furthermore, U will be the motion of the ground. Following the procedure put forth, the first step is to identify coordinates. In this case, we are identifying the motion or the displacement of M2 with the variable y, and the motion of M1, the unsprung mass, with variable x. That's their displacement. And we've defined up to be positive. In this case, and in general in this course, we're going to choose that x equals 0 and y equals 0 when the system is in static equilibrium. In other words, you can sort of imagine that the suspension and the tire are undeformed, but if you set the vehicle down, they will sag under the weight of the vehicle. And so by setting x equals 0 and y equals 0 from this point of static equilibrium, as opposed to from the point where the suspension and the tire are undeformed, it allows us to neglect the weight of the masses in the system. It allows us to neglect gravity. In essence, the weights are being offset by the static deflection of the springs. So there's weight there, but it's exactly offset by the force generated by the static deflection of the springs. In terms of assumptions, we'll assume linear springs and dampers and negligible damping in the tire. The next step in the procedure is to draw the free body diagrams. In general, we need a free body diagram for each independent inertia. So in this case, we'll start with M2. Since we are set up our system such that x equals 0 and y equals 0 in static equilibrium, we do not have to include the weight force. So the only two forces that will be applied to this mass will be the force generated by the spring with stiffness K2 and the damper. In general, a force generated by a spring will be in both directions. If you compress the spring, it will generate a force in one direction, but if you stretch the spring, it'll generate a force in the opposite direction. The way that I like to do it, just to keep myself straight and keep me consistent, is I like to move my mass in the direction, the positive direction I've defined. So what I do is, in essence, I imagine that mass 1 is fixed, and if I move mass 2 in the direction of positive y, that stretches the spring, and so that means that it's going to want to pull down. And so I orient my spring force to be downwards. Similarly, with the dashpot, with the damper, I imagine that that M1 is fixed and that M2 is moving upwards, and since the damping force opposes motion, opposes the direction of the velocity, the damping force will also be downward. We can then express these forces using the linear models that we learned previously. Specifically, the force generated by the spring is linearly proportional to the deformation. Since this spring can move on both ends, its deformation is going to be the difference between the motion of its top point and its bottom point. Therefore, the force will be proportional to y minus x. And again, the force can be downwards or upwards. This ordering, y minus x, corresponds to the downward direction as I've drawn it. In essence, if you imagine that y is larger than x, that force will be positive in the direction drawn. In the case that y is smaller than x, then you're compressing the spring, and then the force, instead of being down, it will be up. Similarly, the force generated by the damper has a similar form, except it's proportional to the relative velocities as opposed to the relative displacements. Your ability to sort of get the hang of defining the direction of the forces and getting the ordering between the coordinates correct, should it be y minus x or x minus y, will take a little bit of getting used to, a little bit of practice. You'll sort of have to sort of explain it to yourself so that you can understand it. There are many more examples out there, in particular in the book, that I encourage you to take a look at to get more practice. Next, we will draw the free body diagram for the mass M1. Again, we can neglect the weight force because of how we've defined our coordinates. And again, there will be a force generated by the spring with stiffness K2 and the dashpot. One way to orient these forces is to apply the same approach that we did with M2. That is, imagine that M2 is fixed, move M1 in the direction of the positive coordinate, which is up, and imagine whether or not the spring is compressed or stretched, and what the direction of the generated force will be. An An alternative is to just point the forces to be equal and opposite of the ones applied to mass 2. In this case, you can imagine if y is larger than x, then you're stretching the spring, and the spring is going to have an equal and opposite force on each end. So if I stretch the spring, the top is going to want to pull down and the bottom is going to want to pull up. And so I can sort of very quickly apply those forces just by using the fact that the two ends of the spring as well as both ends of the damper will have equal magnitude but opposite direction. For mass 1, we will also have the force generated and applied by the spring with stiffness K1. And so again, in this case, we can use this sort of approach where I imagine that the ground is fixed. I move the mass in the direction of positive x. That stretches the spring, thereby applying a force that will want to pull the mass downward. And again, the force generated will be proportional to the deformation of the spring, where the top moves with displacement x and the bottom of the spring moves with displacement u. Therefore, that's an expression for the force generated by that spring. Taking these free body diagrams to the next page, we can then move on to the third step of the procedure, which is to apply Newton's second law in order to generate the equations of motion. If you recall, Newton's second law is sum of the forces equals mass times acceleration, and we will have to do this for both masses. So for mass 2, if we look at our free body diagram, the two forces are Fs2 and Fd. They are both downward, which is opposite of positive y as we've defined it. So the two forces will be negative Fs2 and negative Fd, equal to mass times acceleration, where in this case the mass is m2, and the acceleration of the block we can express in terms of y. So if y is its displacement, then its velocity will be y dot, the derivative of its displacement, and its acceleration will be y double dot, the acceleration of its velocity. So there's an application of Newton's second law to the second mass. We can then substitute in for the two forces the expressions that we show in the free body diagram. And that, in essence, is what we call the governing equation, or the equation of motion for mass 2. We then apply the same process to mass 1, apply Newton's second law. In terms of mass 1, we have three forces, Fs2, Fd, and Fs1. Since Fs2 and Fd are both up, which we've chosen to be our positive orientation, they will be positive, while Fs1 will be negative. The mass of this inertia is m1, and its acceleration will be x double dot. So very similar sort of form to the one we had for mass 2. We then substitute in our expressions for Fs2, Fd, and Fs1 to get that equation, and then we're basically done. That's the governing equation for mass 1. Typically, it's common to rearrange the equations into a form such that all of the like terms are on the same side. So for example, all of the y terms are on one side and all of the x terms are on the other side. So if we do that for the governing equation for mass 1, we get something that looks like this. So we had m1x double dot on one side. We had a negative bx dot, which when we add it to that side becomes positive. We also had a negative k1x and a negative k2x if you distribute that k2. When we move those to the right hand side, they also become positive. On the other side, we can just leave the k2y, the by dot. So those are both positive, and when we distribute the negative k1 and multiply it by the negative u, that becomes positive. A negative times a negative is a positive. And so this is a rearranged form of the governing equation for mass 1. And similarly, we can do the same thing for mass 2. So we have m2 y double dot on one side. We have negative by dot, which when we move it to the right hand side becomes positive. We have negative k2y, which when we move it to the right hand side also becomes positive. On the other side, the negative k2x multiplying the negative x becomes positive. Same thing with the negative b multiplying the negative x dot becomes positive. And so this is the alternative form of that governing equation. So together, these two differential equations describe the motion of this quarter car suspension. Where in general we will need one differential equation for each independent inertia. The last step in the procedure is to attempt to double check things to make sure that they make physical sense. In general, what you can do is you can sort of substitute the values for the masses and the stiffness and the damping, and you can see if the behavior makes physical sense, i.e. The rate of decay or the frequency of oscillation, etc. In general, for a physical system like this, a suspension, which is in essence a passive system, is that it should be stable. The natural system, the natural response of the system shouldn't blow up, i.e. its poles or the roots of its characteristic equations should have a negative real part. If you look at, if you're familiar with some mathematical results, if you have a polynomial such that all of the signs are the same, then it in essence will be stable. You won't have roots with positive real part. And so what we would expect for a suspension system like this is that all of the x terms would have the same sign. They would be all positive or all negative, and all of the y terms would have the same sign. They would be all positive or all negative, the coefficients. In this case, that is the situation that we have. So that doesn't necessarily guarantee that they're correct, but it gives us some indication that we did it correctly, that when we were choosing the orientations up and down and whether it should be y minus x or x minus y, we probably got that aspect of it correct. Here's another example. It is a rotational system. In particular, it's a drive line with the wheel locked. So you can imagine here that this rotational inertia J is the inertia of the drive shaft. Possibly it could be the inertia of a transmission or other elements of the drive line sort of lumped together. On one end of the inertia is an externally applied torque, either from an electric motor or from the IC engine attached to that end. On the other end is fixed, so it's not rotating at all, and so that's the wheel being locked up, the wheel not rotating. And here we have some stiffness, so maybe the drive shaft is twisting, and so there's some stiffness associated with that. And then maybe there's some damping, either due to friction throughout the system, where again that could be the friction lumped together from various parts of the drive line. So the approach for deriving the governing equation for this system is the same as we applied in the previous example. We first define the coordinate and its orientation. So in this case, the motion of the one end of the drive line, the angular displacement, is defined by theta, where that direction of rotation is defined to be positive. We're assuming a linear spring and a damper, and we've also lumped the various inertias and frictions and damping all together into single elements. The second step is to draw the free body diagram. Looking at our inertia, there's the externally applied torque, T, and then there will also be the torque generated from the spring, the twisting of the spring and the twisting of the damper. So there'll be a spring torque and a damping torque. And just as we did with the linear springs, the torsional spring is proportional to the relative displacements of the two ends. In this case, the one end of the spring moves, has a displacement of theta. The other end of the spring is fixed, so the total displacement is just theta, or the relative displacements is theta minus 0, which is just theta. And so the torque generated by the spring will be k times theta, and we've oriented it to be opposite of positive theta. So again, you can imagine that you twist the system in the direction of positive theta, the spring will want to unwind, and so it'll generate a torque in the opposite direction. Similarly with the damper, except that the torque is proportional to the angular velocity rather than the angular displacement. And so that's the free body diagram of our drive line. The third step is then to generate the differential equation from first principles, in this case using a form of Euler's second law, sum of the moments equals J alpha, where J is the rotational inertia and alpha is the angular acceleration. Looking at our free body diagram, the external moments that we have are the applied torque T, which is in the direction of positive theta, so it's positive, and then we have the spring torque and the damper torque, which are in the opposite direction, so they're negative. Since theta defines angular displacement, its derivative with respect to time will give us angular velocity, theta dot, and the second derivative will give us angular acceleration, theta double dot. And so that is the resulting form of our equation. T minus the damping torque minus the spring torque equals J theta double dot. We can then substitute the expressions for TS and TD that we have in our free body diagram to give us this, which is the governing equation for the drive line. Again, it is typical to try and gather like terms on the same side. So here we've got a negative b theta dot. If we move it to the right hand side, it becomes positive. We've got a negative k theta. If we add it to the right hand side, again it becomes positive. And so this is our result. Again, since this is sort of a passive system, we would expect all of the coefficients of like terms to have the same sign, indicating that the roots of the characteristic equation have negative real part, meaning we have exponential decay, not exponential growth. Since the signs are consistent, that gives us some indication that we did this correctly. Just real quickly before we move on, if we look at the purpose of modeling a drive line, it can be especially important when we're dealing with electric vehicles. And the reason that is because with an electric vehicle, oftentimes we don't necessarily need a transmission, and oftentimes we don't need a clutch. You can sort of generate the torque speed characteristics that you want just by the way that you control the motor, by the way that you command voltages or apply voltages or current to the motor. So you don't necessarily need a clutch or a transmission. The presence of the transmission and a clutch tend to add more damping into the system. So electric vehicle drivelines sometimes have less damping than the driveline in a conventional vehicle. And this can lead to sort of more oscillation or more resonance in the driveline, which is undesirable. It can be felt by the driver. It can be even dangerous. Another aspect of that is that the dynamics of an electric motor can be much quicker than the dynamics of an IC engine. So you can generate the torque generated by the electric motor can be applied very quickly. Almost, you could imagine, sort of a step in torque. And so that very quick jump in torque can excite high frequency resonances in the driveline, whereas an IC engine is slower to respond, and it's less likely to excite some of those resonances. So that's another reason why it's especially important to be able to model and analyze the driveline in an electric vehicle. In this example, we will model a brake pedal. That is, we'll determine the governing equation that models the dynamic behavior of this brake pedal. This is something that could be important when designing an electric vehicle, because electric vehicles need to use a brake-by-wire type system in order to allow regenerative braking. With a conventional vehicle, the brake pedal is mechanically connected to the calipers at the wheel, through perhaps a vacuum booster or some hydraulics. But when the driver presses on the pedal, there's resistance, there's mechanical resistance that gives the driver a feel. With a brake-by-wire system in an electric vehicle, you may want to do braking by running a generator. And so there isn't necessarily a mechanical connection to the brake calipers. And so what you want to do is you want to emulate that feedback. You want to give the driver the same sort of feel. So that's one reason why you may want to model the dynamics of a brake pedal. The approach that we'll use is the same approach we've been using. First, we will define a coordinate system and its orientation. In this particular case, we will define the motion of the pedal in terms of its angular displacement theta, and we'll define rotation downward to be, or rotation in the clockwise direction to be positive. We'll assume a linear spring and a light rod. By assuming that the rod is light, we're making the assumption that the mass of the pedal is concentrated entirely at the end. We'll assume that in static equilibrium, theta equals 0. That is, the pedal is horizontal. And again, the reason that we do that is so that we can neglect the weight of the pedal. And the reason that we're able to do that is because the weight of the pedal is exactly offset by the force generated by the spring under static deflection. We will also assume small deflection, and the reason that we do that is so that we can make the assumption that the spring sort of compresses entirely vertically, and the force is applied entirely vertically. If we allowed for larger deflections, then we would have to deal with a situation where the spring gets sort of off at an angle, which would make the problem more challenging. The next step is then to draw the free body diagram. Looking at the pedal, we have this externally applied force from the driver. We also have a force generated by this spring. Assuming that the pedal moves in the positive theta direction, that will compress the spring, causing the spring to push upwards on the pedal. Then there's also the reaction forces of the pedal at the point where it's connected to the sort of the frame. Looking at this system, we can see that it's a rotational system. The pedal rotates. But we haven't defined any torques per se. Our free body diagram has only forces. And so what we need to recall is that forces induce moments. Specifically, the moment induced by a force is equal to the force times the moment arm, where the moment arm is the perpendicular distance from the reference point to the line of action of the force. And that may not make a lot of sense, but I'll try and make it a little bit more clear as we go through the example. So we will also now go ahead and generate the differential equation governing the behavior of this system. Since it's rotational, we'll use the sum of the moments equation, where the sum of the moments is equal to J times alpha, where J is the mass moment of inertia of the pedal and alpha is the angular acceleration of the pedal. We will choose to use the connection point O as our reference point. And one advantage of doing that is that these reaction forces then have no moment arm. Since they pass through the point O, their moment arm is 0, and hence they don't induce a moment. These other forces, the spring force and the applied force, however, do impart a moment. We will define the lever arm for the applied force F as R. Looking at this force, it causes the pedal to rotate downward, which is in the direction of positive theta, so we'll define that moment to be positive. So this is the positive moment induced by the applied force F. We'll define the moment arm for the spring force to be R sub S. This force causes the pedal to rotate upward, which is opposite the direction of positive theta, so we define that to be a negative moment. Alpha being angular acceleration is the second derivative of angular displacement, equaling theta double dot. Looking at this triangle, the horizontal leg of the triangle defines the moment arm for the applied force F. It's the distance from the reference point O that is perpendicular to the line of action of the force F. Similarly, the force from the spring has a moment arm R sub S, where it's the horizontal distance of this smaller triangle. The force generated by the spring, if we recall, is equal to the stiffness of the spring times its deformation. We will define the deformation of the spring to be x. So looking at this, that vertical distance that the spring is compressed we'll define to be x. Looking at this equation, this differential equation, it's in terms of sort of several variables. The moment arms change with time, the deformation of the spring x changes with time, the angle theta changes with time. But what we would like to do is we would like to express the differential equation in terms of a single variable. In essence, this is what we call a 1 degree of freedom system. Its motion is described by a single variable. In this case, we will use the variable theta to reflect the motion of the system. So we want to be able to express the moment arms and the deflections x in terms of theta, and we can do that using geometry. Looking at this smaller right triangle, the hypotenuse is the length L1. That's the distance along the rod from O to the point of the application of the force. So that's the hypotenuse of a right triangle. R sub S is adjacent to the angle theta, so it's equal to the hypotenuse times cosine of theta. The deformation x is the side of the triangle opposite theta, so it's equal to the hypotenuse times sine of theta. You may not remember from geometry, but there was a mnemonic, SOHCAHTOA, that may help you remember how to calculate the lengths of the sides of the right triangle. Similarly, the moment arm for the applied force F, R, can also be calculated as the hypotenuse times cosine of the angle. But in this case, the hypotenuse of the larger triangle is defined as the distance L2. So this whole distance is defined to be L2. Using those values and substituting in, we get a differential equation entirely in terms of theta. Basically, that's the governing equation. We will go ahead and rearrange it a little bit to get this form. Looking at this, it's a little difficult for us at this point to analyze this differential equation, solve this differential equation, because it's nonlinear. It has cosines of theta and sines of theta, which are nonlinear functions. So in order to sort of double check the results, looking at the signs of the coefficients, or looking at the roots of the characteristic equation, it's a bit challenging. Later in the semester, we will discuss how we can analyze a nonlinear differential equation like this, but that's not something we will do quite yet. We will now discuss the use of gears for transmitting and converting motion. For example, a set of gears can be used to change the speed with which an input shaft causes an output shaft to rotate. It can change the amount of torque being transmitted by a shaft. It can even change the direction of motion. The use of bevel gears can change the axis being rotated about between the input and the output shaft, or a rack and pinion can change rotational motion into translational motion. A classic example of where gears are used in an automobile are in the transmission. This red curve shown relating tractive effort to vehicle speed. This sort of torque speed curve is ultimately what is desired for an automobile. At low speeds, we want a lot of torque in order to accelerate the vehicle, or in order to do hill climbing and things like that. But at higher speeds, we don't need as much torque. When we're traveling on the highway, we want to be able to maintain a high speed, but we don't necessarily need to be able to accelerate very rapidly. The problem is if you look at the torque speed curve of an automobile, it's something like this blue line, or the torque speed curve of an IC engine, it's like this blue line, which is very flat, which doesn't give us the sort of behavior that we want. So what you do is you use a multiple gear transmission in order to approximate this relationship where you have high traction at low speeds and not necessarily as much torque at high speeds. It's interesting to note that with an electric motor, you don't necessarily need a transmission like this. You can achieve performance like that indicated by the red line just by the way that the motor is controlled. The simplest gear train is just a single input gear driving a single output gear. The relationship between these two can be understood by making use of the fact that the gears must mesh without slipping. The fact that these teeth can't slide against one another, what that means is that at the point of contact, the velocity at one side of the contact must be exactly equal to the velocity at the other side of the contact. They're not sliding against with respect to one another, so the velocities must be equal. We can also make use of the fact that the velocity at the edge of the gear is equal to the radius of the gear times its angular velocity. If that's something you don't recall, that's okay. So V1 is equal to R1 times omega 1, and V2 is equal to R2 times omega 2. Dividing through by R1, so dividing R1 to the right hand side and dividing omega 2 to the left hand side gives us the relationship between the input speed and the output speed, and it's shown to be inversely proportional to the radii. Making note of the fact that the geometry of the gears need to be consistent in order that they mesh correctly, the number of teeth, which we will represent with the variable n, must be proportional to the radius. So the ratio of radii r1 to r2 is equal to the ratio of the number of teeth n1 to n2. In terms of the torques, we can understand the relationship between the input torque and the output torque by making the assumption that there are no losses in the transmission. So T1 times omega 1, the torque applied to the input shaft times the speed of the input shaft, is in essence the power input to the gear train, and T2 times omega 2 is the power out of the gear train. If we divide T2 to the left and omega 1 to the right, we get a relationship between the torques and the speeds. And then, taking advantage of the relationship on the previous slide, we can see that the torques are proportional to the number of teeth on the two gears. And so what we see here is that there's a trade-off between speed and torque. So if this larger gear is our input gear, the output gear will rotate at a faster speed, but with a smaller output torque than the input torque. So that's sort of the trade-off. You get a higher speed but with less torque. The opposite is true if your input gear is the smaller gear and the output gear is the larger gear. We can make a more complex gear train by putting a set of gears in series with one another. So considering omega 1 to be the speed of the input shaft and omega 2 to be the speed of this intermediate shaft, we can relate omega 2 to omega 1 using the ratio of teeth of the gears as we did on the previous slide. We can also use the same sort of notion to relate the speed of the intermediate gear omega 2 to the speed of the final shaft omega 3, where again the ratio of the speeds is inversely proportional to the number of teeth. We also know that this omega 2 can be expressed in terms of the initial input omega 1. Substituting that expression in, we get that. So if we look at these two sets of gears in series with one another, and we treat omega 1 as the input, the speed of the input shaft, and omega 3 as the speed of the final output shaft, the gear ratios multiply. And this relationship can be helpful understanding this. Systems of gears like this are important for hybrid electric vehicles in order to couple the power from two different sort of sources. In particular, coupling an IC engine with an electric motor, for example. With a series architecture, the two power plants are coupled electrically. The IC engine is generating mechanical energy. The battery is a source of electrical energy, and the way that they're combined is that the IC engine is connected to a generator. Thereby, the mechanical energy of the IC engine is converted into electrical energy, and that energy can then be combined with the electrical energy from the battery. Conversely, in a parallel architecture, the two power plants are coupled mechanically. So the IC engine, is generating mechanical power. The battery is generating or putting out electrical power, but it's converted into mechanical power by driving a motor. And then the mechanical output of the motor is combined with the mechanical output of the IC engine using some set of gears or pulleys, etc. in this analysis we're going to assume that power is conserved. So for example, T1 omega 1 could be the power coming from the IC engine, and T2 omega 2 could be the power coming from the electric motor. And we're going to combine those two mechanically to generate some output power to the wheels, T out times omega out. The way that this coupling is done, we can use what we call either a speed coupling device or a torque coupling device, and I will try and explain these two concepts on the following slides. On the previous slide, we had that omega out times T out equaled omega 1 times T1 plus omega 2 times T2. The relationship between torques with a torque coupling device, in essence, we take that omega out and we divide it to the left-hand side such that we have omega 1 divided by omega out, and K2 is omega 2 divided by omega out. And we'll understand these constants in terms of the geometry in a second. An example torque coupling device is a series of gears or pulleys like this. So for example, omega 1 could be a shaft connected to the IC engine, and that gear is pushing on the output gear, and then the electric motor could be attached to this gear N2, which is also in essence pushing on the output gear. And so the fact that both gears are pushing on the output gear, you can get some sort of feel for the fact that the torques are going to add. And so that's why this is called a torque coupling device. This kind of device we define as having 2 degrees of freedom. So that's what DOF is, degrees of freedom. And that comes from the fact that this relationship here, we have a single equation with 3 variables. And 3 variables minus 1 equation equals 2 degrees of freedom. And so what that means is, in essence, we can set the torque of the IC engine to be whatever we want, and we can set the torque of the electric motor to be whatever we want. And so those 2 degrees of inputs are free. But once we set T1 and T2, the IC engine torque and the electric motor torque, then the output torque is defined. So we don't have control over that. So that is how we come to the definition of this as being a 2 degree of freedom system. In practice, however, there's only 1 degree of freedom that we can play with. And so think about why that is for a second. The reason that is because in practice the output is determined by the demand of the driver. When the driver steps on the gas, when he steps on the accelerator pedal, he is in essence requesting a certain amount of torque at the wheels. And so T out is chosen by the driver. Therefore, we can choose the IC engine to be whatever we want, but then in order to get the output requested by the driver, then that completely determines what the torque generated by the electric motor must be. So we can define one of the 2, but then the other one will be constrained by what the driver's requesting. Looking at this relationship between omega 1 and omega out and omega 2 and omega out, we have again this sort of fact that the speeds at the input or at the contact surfaces must match. So just like in the previous slide, we had the relationship that the speeds were inversely proportional to the number of teeth. That's also what we have here. So the speeds are constrained by the no slip condition, and omega 1 over omega out is the inverse of the number of teeth of those two shafts, the gears attached to those two shafts. And similarly, K2 is equal to N3 over N2. Another type of device that we can use to combine the two different power plants is what we call a speed coupling device. So again, if we still begin with our original equation where we were assuming power was conserved, where we had T out times omega out equals T1 times omega 1 plus T2 times omega 2. If we divide through by T out, we get that K1 is equal to T1 over T out, and K2 is equal to T2 over T out. The sort of device that achieves this speed coupling is called a planetary gear set. And so in this case, we can sort of imagine that the IC engine is connected to this gear, which we call the sun gear, the central gear, and let's say the electric motor is connected to this outer gear, which is a ring. And so if we think about this, for example, if the ring was fixed and the IC engine was running, turning this central gear, it would cause these outer gears, the planet gears, which are connected together with a yoke, to move at a certain speed. So if the IC engine's moving with a certain speed, that'll cause the carrier to move with a certain speed. But if we then allow the ring to also move, i.e. it's connected to the electric motor, then that will cause the carrier to move even faster. So if you have the sun spinning and the ring spinning, then those two speeds add, in essence. And so that gives some sense of why this is what we call a speed coupling device. The relationships between the various speeds of these different gears again goes back to this no slip condition, where the velocities at the point of interface must be equal because the gears mesh without slipping. And we won't go through it in this class, but you can derive these relationships by using this no slip condition and the geometry of the system. The torques are constrained by power conservation as we defined up here. In general, you can combine a system to have both a torque coupling device and a speed coupling device. However, you can only use one at a time unless you add an extra power plant. So for example, you could have a system with a speed coupling device and a torque coupling device, and you could operate them one at a time, perhaps using a clutch or something like that. But if you want to use them both at the same time, then you need to add another power plant. A common sort of architecture that combines the use of a speed coupling device and a torque coupling device using an extra power plant, which in this case is just another electric motor, which we'll call a generator, is shown here. And this is typical of what we would call a parallel series implementation. And it basically, by including both with this extra power plant, you get the advantages of a parallel architecture and a series architecture. You get 2 degrees of freedom as opposed to just the 1 degree of freedom that the individual architectures offer you. In essence, you can operate the engine and the motor independent of one another and independent of what is being requested at the wheels. So this specific example, the engine is connected to the carrier, the planet gears, the generator's connected to the sun gear, and the output is connected to the ring gear. By using this architecture, you can set the engine to operate in its sweet spot, which is something that you couldn't do with a parallel implementation, a straight parallel implementation. There you were basically constrained by what the driver was requesting and by what the motor was doing. But in this case, you can operate the engine at its most efficient region, here it being connected to the carrier. If the sun was fixed, if we didn't have the generator, if you ran the engine at a certain speed, it would completely define the speed at the output. But by having this extra power plant, you can run the generator to move the sun, thereby achieving basically a CVT, a continuously variable transmission. So the relationship between the engine speed and the output speed can be set anywhere you want it. So this sort of overcomes one of the disadvantages of a parallel implementation, but it also overcomes the disadvantage of a series implementation. So in a series implementation, you could operate the engine in its sweet spot, but in order to do that, the engine drove a generator, which then generated electricity to drive the electric motor. And so in that series architecture, that multi-form conversion, going from mechanical to electrical and then from electrical back to mechanical, caused unnecessary efficiency losses. Every time you did a conversion, you lost energy. But in this situation, you can operate the engine in its most efficient region without having to do that multi-form conversion, because the engine is mechanically connected to the output. You don't have to convert it to electrical and then back to mechanical. This sort of architecture is quite common. A lot of Ford vehicles use it. They call it the power split architecture. The Prius vehicle also uses this sort of architecture, the Toyota Prius. This concludes Module 4. In this module, we looked at the modeling of mechanical systems. In particular, we studied the various elements of a mechanical system, inertia elements, spring elements, and damper elements, looking at how to model them. We then used first principles to determine the governing differential equation for a mechanical system. The approach we used was to first choose a coordinate system and orientation, make any assumptions or define any assumptions that we are going to do in the modeling of the system. We then drew the free body diagram, the FBD, and then applied Newton's second law, sum of the forces equals mass times acceleration, in the case of a translational system, to derive the governing equation, or the rotational analog, sum of the moments equals J alpha. We also looked at gears for transmitting and converting motion. We looked at simple gears, complex gear trains. We also looked at a planetary gear set for performing speed coupling, two power plants in a hybrid electric vehicle. We also looked at gear sets for torque coupling. And finally, we discussed using a parallel series architecture that combined both a speed coupling device and a torque coupling device through the addition of a third power plant.